we'll make our mass 1. So I get 1,000 squared over 100, which is,
1,000,000 over 100.
so 10,000. The normal force would therefore be 10,000 divided by sine of 70 degrees plus 0.6 times the cosine of 70 degrees, which is
About 8,732.25.
I got
35, sorry.
I got 34.
34.
that's 34 there?
Yeah.
Yeah.
Oh, I'm
0.35.
sorry. Yeah, no, I said that wrong.
Okay.
Wait, no, 0.35.
0.35, yeah.
Yes.
Yeah.
We good now?
Yes.
All right. So we have, the normal force has increased dramatically. We have a weight of around 10 newtons for this car, and a normal force of significantly more. So the faster it goes, the more it's pressed up against the more it's pressed up against it. The friction force, or at least the component that's down, the friction force here, if I'm at that maximum, is 0.6. So Fs max, 0.6 times that 8,000, 873435, 8734.35.
$5,240.61.
5,240.
0.61.
Wait. So, we already know that there is no top speed rate?
That, well, we're sort of playing around with the numbers just to see what we get.
Okay.
That, so the centripetal force,
Okay.
well, actually, let's do the vertical forces. So y, so up, I've got y cosine theta. So 8734.35 times the cosine of 70.
So our number times 70, cosine 70?
Yes.
2,987.32.
Yeah, 32, right?
3G.
Yeah.
All right, so the friction that is acting in that direction would be the cosine, so that's Fs cosine theta, which is 5,240.61 times the, oh wait, something got messed up there. Oh, this should have, I'm doing vertical.
Oh, so.
So Fs sine theta would be 5,240.61 times the sine of 70 degrees, which I would think was going to be 2,977.22.
About 4,924.
Yeah. Yeah.
Yeah, that's what I got. Point 5.6.
0.56.
Something is wrong. Because y cosine theta is the vertical, that's what's up. This is accelerating downwards.
Oh. Huh.
Don't make no sense, does it?
Oh. We are working under the assumption that the static friction is at its maximum static value. This is the maximum it could be, but we don't need that much.
That's the
Or
max.
that's the maximum it could be, but we don't need that much. We only need enough static friction to keep it from sliding. So this would be, so that's the maximum value there, but it actually would be 2977.22 newtons. Because this plus the weight is what's going downwards and that's what's going up. That they would have to equal each other. Again, I said mass equal to 1 kilogram.
Where'd you get the 8,734.35? What is that?
That is the normal force
Oh, okay. I see.
that from over here.
I see.
And we have built in several places this idea that we're at our maximum friction.
That we're under, oh, that we're under.
So, but conceptually, so what I'm picturing conceptually, unless something else pops in, the faster you're going, the greater the normal force is, which increases the friction,
Yeah.
which makes it harder to slide. That's my rationalization. So just so long as you're going above 28.19 meters per second, you won't slide.
It does, like theoretically. That makes sense.
But it's another lesson to me to, work through the problem before I put it on a test, for example.
So
This
basically,
is fun though.
Work it through more than once, I should say.
the maximum velocity is like
Maximum speed.
28.19, like, is less than, like, the maximum speed.
The maximum speed
It
is
would be-
greater than that.
Yeah, it would be, infinitesimally, just a little bit more, it would.
No. This is the minimum speed, so go a little bit just below this and you should start sliding down the ramp. But as far as sliding up the ramp, from what we have right here, you could go as fast as you want. And
Oh,
You will
okay.
you won't slide up the ramp at all.
But at some point, we would slide up there, and we just don't know that, based on the information that you give us.
Yeah.
Oh, it would at some speed?
It
Because I didn't even think about sliding up there.
It's supposed to at some.
But think about that, 70 degrees is rather steep.
That's what I was thinking, when it would push it down against the ramp, so you'd have more traction. And
Yeah.
it wouldn't slide up,
Yeah.
because of how steep that is.
I'm gonna guess that you would need some sort of downforce though. If you go way fast, if we're talking about going as fast as we are, like if we tried it, we'd need
Oh, that, just the aerodynamics.
like
of
the
how it-
aerodynamics for it to work out. Like
Yeah.
we need a spoiler and make sure that no air gets under the car. The suspension would have to be firm enough. But yeah, theoretically.
Air resistance is a myth, that's why we don't do much with it.
Is it a myth?
In this class, apparently.
Air resistance is incredibly complicated. I do have a video, I think I have it under the forces because we're using F equals ma as a starting point. But I think at this point, you can deal with it. If you went into the chapter 4, chapter 5, I do have a couple videos with drag, so that you can see what you're missing by not going over it here.
So if you took, I'm just curious, so like what would, if you did take the square root of the value and you got an imaginary number, what would that mean theoretically? I know it couldn't happen in real life, but like what would that mean?
Okay,
Well,
assuming that there's no mistake, a negative under the radical means that there's not an answer.
Oh,
So,
okay.
in this particular case, it would mean that there is no maximum speed.
Okay.
So if that happens on a test, we put NA.
Or no maximum.
We do all that work for nothing.
Dude, we found the minimum.
Yes, on a test, you would put in A, making sure you show your work about how you got that, as opposed to you just felt like writing in A next to one and got lucky.
But would you pay that to us?
It is not my intent to do that on a problem like this.
Okay.
As you saw, that was not my intent to come out with, there is no maximum speed. However, I have done problems where when I'm working through the solution, I get an answer, but I made a careless error and didn't realize later that was a rather major error I made. Because I might have decided the wrong spot, and we would have gotten a very different answer.
How do you figure out that you messed it up? Like all the students get it wrong and then double check it?
There is a certain amount to that. Usually when I'm marking a problem wrong, I then try to figure out where the problem was. And and there have been problems where I'm working through, I can't find any mistakes in what the student has done, then I look at my work and go, oh, yeah, there's a mistake right there. And then I go back to whatever I've graded already for that problem and regrade. So that's how I handle it. There was one situation where I made a careless error in my solution and didn't catch it, handed them all back, and eventually someone came back and said, I was working with a tutor and they said that there's no possible answer to this. And my first thought was, of course there's an answer to this.
Oh,
And then I realized, oh, yeah, I see what I did wrong. So, in that particular case, since they were all graded, I think I just threw the question out and then went back and recalculated everyone's grades. I will say, there were 3 students who actually made the same mistake I made, so they've gotten full credit for it.
Oh, nice.
And when I threw the question out, I looked at what their grade was before, what their grade is after, whichever one was higher. That's the one they got.
I think, so apparently the steepest banks that are actually used in like racing, the steepest one is 43 degrees.
Yeah, that track
So
was
maybe-
abandoned at this point.
Yeah, so that makes sense now.
Okay.
Yeah, so it would be something crazy for you to start going up because it is too steep. Now it's. So I think you're right. There shouldn't be a max.
It actually, you know,
Yeah, I'm also.
I was just curious. I'm like, what? Is there even a 70-degree ramp anywhere?
Well, we just saw it.
Oh, that one was?
They said it goes up to 78 degrees at the top.
Oh.
That's why it picked 70.
That's what it was. I forgot about that. So my bad.
So we proved that that was pretty safe what they were doing on the trail.
Yeah, very safe.
Yeah.
Yeah.
Despite all the-
Sure.
So they could have gone faster. They were just.
Yeah, the faster you go, the better.
Yeah, they were just
It was
skipping it
really
on
those
us.
bumps. If they would have smoothed out those bumps, they could have been going.
Yeah.
Yeah, then you get into issues of more reality of air resistance and car lifting up or tire blowing, hitting the pothole.
Little potholes
Yeah.
everywhere.
Oh my God.
Yeah.
So that-
You know
that's
how
what
scary
it's
that would be?
completely
You take an
flat.
F1
Yeah.
car and get air under it, you're just.
Like
That's what I'm
perfectly
saying.
flat.
Yeah, our example, one, it wasn't warped like that, it was just a flat, and that there's no air resistance, so I'm not worried about the design of the car, whether the car is gonna lift up or not.
Yeah.
I'm sure you've seen that video of the car, it's like, and just starts flying.
Yeah.
Yeah. That was one of the scariest things that I had seen for a while. I was like, because I was so hyped, I was like, I want to drive one of these one day. And then I saw that accident, and I'm like, yeah, I think I'm good.
Any questions before I move on to a newish topic?
I have one. If you move to that 10,000 or sine of 70 plus point, where'd you get the sine of 70 plus 0.6 cosine?
I was playing around with the numbers, and I said, let's just suppose we're going 1,000
Yeah.
meters per second, what happens. So that's where the 10,000 comes from. The other is you factor y out, and I'm left with y times sine theta plus mu s cosine theta.
Okay.
And then I divided by the sine theta plus mu s cosine theta.
Okay.
That's where that comes from.
Oh, okay. That's where I thought it came from. I wasn't sure.
All right, any questions? And just to let you know, I'm not gonna derive Kepler's laws in the room here. I've done videos for it. I did a deriving E equals MC squared once. There's a lot of complex math in the technique I was using at that time, and that took 3 hours. There are shorter versions, which we will get into, 252. But Kepler's laws it's math gymnastics. So if you're interested in it, the videos are available. And one of those videos of converting from polar coordinates to, it wasn't polar coordinates, rectangular, to elliptical coordinate system. My most popular video.
How many views?
Oh, yeah, I was gonna ask.
Over 2,000.
Oh, dang.
Considering most of them are, like 5.
So why, what is the reason that so many people?
I
probably
have
outside
no
of this
idea.
class needed to watch
The
this?
YouTube algorithm, man.
For the same reason that I've had one of my videos banned in 4 countries. It's the one where I am showing a video, it's not copyrighted material, so it's not a copyright issue, but I'm showing the Tacoma Narrows bridge collapse. And I'm wondering if some countries have a ban against showing bridges collapsing or something. That's the only thing I can think of.
It wasn't even like the monkey shoot one? Like-
No, not the monkey shoot.
That's disappointing.
Was that the bridge that like waved?
Yep, that's the one.
That was crazy.
All right, so let's get into gravitation. We've talked about the force due to gravity already. In other words, the weight of an object is equal to mg. And that works fine as long as you know what g is. And it doesn't really count as weight. You don't really talk about the weight of the moon. There's a gravitational pull between the moon and the Earth, but it's not a weight. So, when we are dealing with on sort of an astronomical or on a tiny level, the gravitational force has a different equation. So first off, when dealing with physics, Newton's third law, for every force, there's an equal and opposite force. In other words, if I have 2 objects and there's a force between them, I should be able to just switch the objects and the magnitude of the force stays the same. So the force between me and the Earth is the same as between the Earth and me. Semantics issue there. But the Earth pulls on me with about 200 pounds of force. I pull up on the Earth with 200 pounds of force. It is just as legitimate to think of I am standing on the Earth as I'm balancing the Earth on my feet. So the force due to gravity in general does deal with both masses, but whatever operation I have going on between the masses has to obey the commutative law. And we have 2 basic operations which commute easily, addition and multiplication. So I'm either going to add the masses or multiply the masses, and it's multiplication. And the bigger the mass, the bigger the force. So I've got my 2 masses here. Obviously I can set it up for other things. Now, not necessarily thought of at the time, but if I have 2 masses, they'll be attracted to each other. How does one mass know the other mass exists?
They look at each other.
Sentience in subatomic particles, okay, that's a possibility.
Like, I don't know, I'm very unfamiliar with this topic, but it messes up the space-time fabric or whatever.
Does it have anything to do with the charges of?
Yeah,
these
that was
masses?
my next guess.
Like electrical.
All right, so 2 things here. One, yes, that's when you get into general relativity. We're not there yet.
I'm
So-
not even close.
Yeah, there is actually, the mass warp space, and what you do is you feel the warp. But I want to avoid that for the moment. That's a 20th century thing, and we're still in the 1700s.
Oh,
This is
Okay.
classical physics we're doing here. All right, now the issue of, what was it?
Charges.
All right, so they're not, mass doesn't have a charge, but I have seen various things which sort of pretend there is, but we just generally call it mass. Charge is a misleading term there, so I want to steer clear of that for the moment.
So
Well, actually, I can steer clear of that for the whole course.
So don't say charge, don't.
Don't say charge till you're actually talking about electric charges.
So no bonds.
No, I mean, what's the bond between me and the Earth?
No, there's none. The gravity, I guess, but no, there's none.
Yeah, but how does the Earth know I'm here?
That's what it's saying, some sort of charge. I don't know.
Well, you're pulling on
Maybe I'm
it.
special.
Maybe you are.
We're all special. The Earth loves us all and wants to keep us near.
So if it doesn't like someone, they just.
I bet if you got the Weekly World News, there'd be somebody, there's an article in there somewhere of somebody suddenly projecting off into space.
There was that one guy that got struck by lightning twice in a week.
Wow.
And he still made it. That was the crazy part. But Earth didn't like that. That's what I'm saying.
All right.
But why?
All right, so if we're ignoring the warping of space by a mass, the physicists had to come up with something. So they had this idea that each mass gives off something. Gravitons is what they call it now. But this idea that there's something being given off by a mass that the other mass senses. So if I got a universe here, I have a mass all by itself and it's giving off something.
Okay.
Think of it. No one other than, probably the only one who will use this term, but mass pheromones. This other mass senses it and goes, ooh, there's something there, let me track it. Let me see what's there, what's the source? In what's called field theory, these would be called the gravitational field, that's what's being given off. In more modern quantum physics, it's giving off gravitons, and that's just a particle.